Welcome to day 2 of Unit 3. Today we'll be talking about the derivatives of logarithmic functions and inverse trig functions. So to get started, we do have to talk about the derivative formulas for logs and for inverse trig functions. So I have the first derivative formula written up, and all of this information is in your textbook. In fact, I haven't written all of the inverse trig functions out, just the 3 big ones. So the derivative of a log with base of a of x is just 1 over x natural log of a. Now what I think is pretty cool is using this formula for the derivative of a log with base a, we can find the derivative formula for the natural log of x. Remember, the base of the natural log is e, so we have 1 over x times the natural log of the base. And in this case, the base is e, and the natural log of the natural log of e is 1. So the derivative of natural log of x is just 1 over x. Okay. The derivative of inverse trig functions are a little scary looking initially, but these are the 3 big ones that tend to pop up. But you should be prepared for the AP test to see the inverse of cosecant, cotangent, and secant. But these are the ones that we'll probably use most often in our class. So the derivative of the inverse of sine is 1 over the square root of 1 minus x squared. Okay. Sine and cosine are so closely related that the derivatives of their inverses are very similar. The only difference being the negative sign for cosine. And the derivative of the inverse of tangent is 1 over x squared plus 1. So for the first 2 examples, we're going to look at some logarithmic differentiation. So you'll come to find that differentiating anything with natural log is fairly simple. The derivative is 1 over whatever's in the argument. And then, of course, there is a chain rule here because the inside function is more than just x. So I must multiply by the derivative of the inside. The derivative of the inside being negative 1. Okay. For b, following along with my formula that you saw on the previous page, I have 1 over the argument times the natural log of the base. And then yet again, there's another chain rule. The derivative of the inside is 5x to the 4th. So a little cleaner. 5x to the 4th over the natural log of 4 times x to the 5th minus 7. Okay, so for part C of example 1, I want to first show you a little trick called logarithmic differentiation. It's something that's not necessarily assessed any longer on the AP test, but can come in very handy. And where it's going to come in into play the most is when I have a problem like this. Some constant raised to the power of x, or some other function, x squared, whatever. So we don't have a derivative formula for this. And I can't use power rule because the power rule is for functions that look like this. The power rule is used for a function x raised to the power of a constant. And here we have a constant raised to the power of x. But what I can do is use my log rules and take the natural log of both sides, remembering that the natural log of something raised to a power, that power can come down in front. And now I just have the natural log of a, which is just a number, just a constant, times x. So using implicit differentiation from last class, the derivative of y with respect to x is just ax times the natural log of a. So, applying that formula to this problem, the derivative of h of x should be 7 to the negative 2x times the natural log of 7. However, notice what was in the top, what was in the exponent is not just x. So chain rule does come into play here. Multiplying by the derivative of negative 2x, which is negative 2. Okay, so for the last part in example 1, we're going to look at the derivative of an inverse trig function. Now there's a chain rule here, and I tried to make this very clear that inverse sign was on the inside and the function squared is what's on the outside. So let me get a different color. Y prime is the derivative of the outside times the derivative of the inside. And the derivative of the inside is the derivative of the inverse sign. Okay? And that just comes from the derivative formulas that, yes, you will have to memorize. Before we move on, something that I would like to make a note of is, what if what was inside inverse sine was something besides just theta or x? What if it were something like 3x? Well, whatever's inside of the argument for sine is what is being squared under the radical sign in the derivative. So this derivative would be 1 over the square root of 1 minus 3x squared, which is 9x squared. I just wanted to make that clear before we moved on. And of course, Mr. Southard forgot the chain rule. So here, the chain rule would be times the derivative of 3x, which is 3. Okay, taking derivatives of logarithmic functions to the next level, let's find the second derivative. So first thing I noticed is that I have a product rule. So the first derivative is the first times the derivative of the second plus the second times the derivative of the first, which is just 1. So y prime is 1 plus the natural log of x. Where'd the 1 come from? It's x divided by x. So the second derivative is 1 over x. As we all know, trig functions are not the only functions that have inverses. Most functions, in fact, do have inverses. So we do want to be able to concern ourselves with or develop a formula for finding the derivative of the inverse of a function. And we can do this if we remember that by composing a function with its inverse, we expect to get x. So this is a true quantity. Now, applying the derivative to this, I get the derivative of the function composed with its inverse times the derivative of the inside, which is the derivative of the inverse, equaling 1, because the derivative of x is 1. Now, solving for this quantity, the derivative of the inverse of a function is equal to 1 over the derivative of a function evaluated at its inverse. And so this is the formula that we'll use in the upcoming examples. Alright, so our first example is one of the easier kinds of examples, where I'm actually given some values, and then I'm asked to evaluate the derivative of the inverse of a function at a specific point. So, I want to know this, and I have my formula, I've written it up there. So the derivative of the inverse, of 1 should be 1 over the derivative of the inverse of 1. So now I just have to plug in my values. Well, it doesn't look like I've been given the inverse of 1, or the inverse of f at 1, but I do know that f of 2 is 1. This implies that the inverse of 1 is 2, because the inverse of a function flips the domains and ranges. So I have 1 over the derivative of f at 2. That I do know. And so there's my answer, 4/3. So now for an example that's a little more difficult than the previous, still dealing with finding the derivative of an inverse of a function. And what I'll do first is show you sort of an analogous method as the previous example. And in the upcoming example, we'll show you a little bit more of a brute force style of solving the problem. So first up, I'm still going to be using that formula. I'm asked to find the derivative of the inverse of f at 6. All right, so the derivative of the inverse at 6 is equal to 1 over the derivative at the inverse of 6. All right. So what I have to find out is the inverse of the function at 6. All right. In other words, if f is my function, I want to know what value of x will give me 6. And in this case, it's 2. 2 squared is 4, plus 2 is 6. So f inverse of 6 is 2. Now it's just a matter of finding the derivative of f. Okay. And f prime of 2 is 4. So my answer is 1/4. So for the final example today, we're going to look at another function where I'm interested in finding the derivative of its inverse at a point. Okay. So I'm going to do this one a little bit differently at first, and then we'll go back and use the formula to see that we do, in fact, get the same thing. So I want the derivative of the inverse, so why don't I go ahead and find the inverse by flipping x and y, and then using implicit differentiation to find its derivative. Okay. Solving for y prime, I get 1 over 3y squared plus 1. Oops, not that plus 1. The derivative of 1 is 0. Alright, so this is what I'm looking for. This is the derivative of the inverse. So what I still need to be able to plug in here is I need the value of y that gives me 11 in this case. So at x equals 11, what is y? Now this is a little bit more difficult to solve. The answer is 2. So I get 2 squared is 4, times 3 is 12, 1 over 13. All right. Now let's go back and use the formula. See if we get the same answer. So I want the derivative of the inverse, which is f prime of the inverse of x. Okay, again, f prime of f inverse of 11. So the inverse of 11 is the value of x at which the function is equal to 11. So if this were 11, what would x have had to have been? Well, I can try 1. 1 cubed is 1 plus 1 plus 1. That gives me 3. That doesn't work. Let's try 2. 2 cubed is 8 plus 2 is 10 plus 1 is 11. So x must have been 2. Okay. And then the derivative of f oops, that should have been a 3. We do, in fact, reach the same answer both ways. I, for one, would just prefer to use the formula in most cases. But in either instance, you do have to be able to figure out the value of x for which you're given that point.